My name is Ayla Gafni. I'm an assistant professor at the University of Mississippi, and in this video, I'm going to talk about some asymptotics of restricted partition functions. So first of all, what is a restricted partition function? Well, a partition of a number n is a way of writing n as a sum of other integers. We write it in non-increasing order, and for a restricted partition function, we're going to restrict to a specific subset of the integers. So take a subset A of the natural numbers, and the only requirement is that the GCD of A is going to be 1. And then we'll let PA of n denote the number of partitions of n where all the parts are coming from A. So for example, we could take A to be the set of squares. And then if I wanted to partition 10 into perfect squares, there would be 4 ways to do that, as seen here. And so that means that PA of 10 would be 4. And what I want to know is, for which sets A can I find asymptotics for PA of n? What do I need to know arithmetically, analytically about the set A in order to study the asymptotics of PA of n? Now, restricted partition functions have been studied extensively over the past 100 years or so. And so the examples that I'm going to give are not exhaustive, but they'll give you an idea of what these sort of asymptotics look like. So here's some examples over the last 10, 15 years of restricted partition function asymptotics. So there's a lot on this slide, and I'm going to unpack it for you a little bit. So we have 5 results, 5 different classes of sets. We have perfect kth powers. We have powers in a residue class. We have values of a polynomial, which is actually a generalization of the previous 2 results. And then we have primes and powers of primes. And so for each of these 5 asymptotic formulas, they all take a very similar sort of format, which is that we have a constant and then an exponential and then divided by a power of n. Now, in the case of primes and prime powers, we actually have also divided by a power of log n, and that's because of the irregular distribution of primes, but we don't need to worry about that right now. Now, in the exponential, we also have something very similar. We always have a constant times a power of not n, but a power of the growth of the function. So the number of elements in our set that are less than n to the power k over k plus 1. So that's what's happening here inside the exponential. And that's where the dominant part of the growth is. And all that matters is how many elements there are in your set up to n. As we can see, all of these restricted partition functions have a similar asymptotic formula format. And moreover, they actually are proven using a very similar version of the Hardy-Littlewood circle method. So what I'd like to do in the next few minutes is go through a very rough outline of what that method is and see what pieces we need to know about A in order to make that process work for another set. So as with any Hardy-Littlewood circle method proof, we need to start with a generating function. And the generating function for restricted partitions is given by this infinite product of geometric series. And it's not so convenient to work with an infinite product, so we're actually going to take a logarithm, and that's going to give us this generating function written as the exponential of this auxiliary generating function here, which is now a double sum. And then we can use Cauchy's theorem to extract our coefficient of z to the n, which is given here. So now we have the number of partitions of n with all parts in A is given by this integral. And I've written it in polar coordinates. So rho is the radius and then alpha is the angle. We want our radius rho to be close to 1 as n tends to infinity. And I'm going to quantify that by writing rho equals e to the negative 1 over x. So throughout the next slides, I might interchange freely between rho and e to the negative 1 over x, so where x is some large parameter. And as usual, we have our number theory notation that e of alpha is e to the 2 pi I alpha. So now we've got our integral set up, and we're ready to proceed with the circle method. As we know from the summer school earlier this year, we would traditionally divide our integral up into major arcs and minor arcs. So the major arcs would be the pieces that are close to rational numbers, and they would make up the main term of our asymptotics. And the minor arcs are everything that's left over, and they would be error term traditionally. Now, in the case of restricted partition functions, we actually divide the integral up a little bit differently. We're going to divide into 3 parts. The first part is the major arc at 0, which I'll call the principal major arc, and that's alpha very close to 0. And that is going to be the only piece that's going to go into the main term. Then from there, we have the non-principal major arcs, which is all of the other major arcs except for the major arc at 0. And we have, so that's here, the non-principal major arcs, and we have the minor arcs, which is everything else, the leftovers. And the reason that I've split it up in this way is that even though these non-principal major arcs are error terms, they're not minor arcs. I'm going to treat them like major arcs. There are different techniques for the circle method for what we do for major arcs versus minor arcs. And so these non-principal major arcs are treated like major arcs, but then ultimately, instead of getting a precise asymptotic estimate, we just get an upper bound and we shovel it into the error term. So that's how we're going to proceed. We have 3 pieces of the integral, and each of these 3 pieces is going to require a different piece of information about our set A. So I'm going to go through very quickly each of these 3 regimes to see what piece of information it is that we need about A in order to move forward. So let's start with the principal major arc. So here's phi, and if we're on the principal major arc close to 0, then rho E of alpha may as well just be rho, since alpha is 0. And so remembering that rho is e to the negative 1 over x, this is the definition of phi of rho. And I'm going to expand it out using a Mellin transform and then move the sums inside. So this zeta is coming from the sum over j. And then I have moved the sum over A inside. And the goal, the way that we're going to get our main term out of this, is to take, move the line of integration as far left as we can and take a contour integral. And in order to do that, we need to know how this sum, this special zeta function related to A, how that behaves. We need to know about analytic or meromorphic continuation. Are there zeros? Are there poles? What are the residues at that pole, those poles? Are there other types of singularities that we need to avoid? All of that is important information so that we can study this contour integral. So that's the first piece about A that we need to understand, is how does this special zeta function behave? Then we move on to the non-principal major arcs. And for the non-principal major arcs, we have alpha being close to a rational number. So R over Q is going to be the rational number, and then beta will be the wiggle room. And here I've written out the definition of phi, again, using rho equals e to the negative 1 over x. And I've just divided the exponential up into the piece that is the rational part and the piece that is the wiggle room beta part. And then I'm going to split this sum according to residue classes mod Q. And when I do that, then all of the dependence on A is now isolated into this innermost sum, and is a sum over the elements of A that are in a specific residue class. And so in order to bound this whole function, I need to understand how A behaves in the residue classes mod Q. If I understand how many elements there are in each residue class, then I can handle this using Abel summation, for example. So that's the next piece of information that we need, is the distribution of A in residue classes. Once we have that, then we're ready to move on to the minor arcs. And for the minor arcs, all we know is that alpha is not in a major arc. So we need to estimate phi for a generic element at alpha. And so here's our definition of phi. And I'm going to expand this exponential into an integral and then move the sum over A inside. And so when I do that, then now, again, I've isolated the dependence on A into this innermost sum. And so to evaluate this entire function and to bound it, I need to bound these Weyl sums, these exponential sums over elements that are weighted by the elements in my set A. And there are a lot of estimates on these. They exist quite frequently in the literature for various sets. So if you happen to have a set where these vowel sums have already been studied, then your minor argument should actually be quite straightforward in that case. So to summarize, we have 3 pieces of information that we would need to know. So let's say you had a set A and you wanted to know, can I find asymptotics for PA events? So as I mentioned before, we've already had kth powers, we've had primes, we've had powers of primes. But what if you had another set in mind and you wanted to know, can I use a similar method to find the asymptotics of the restricted partitions into that set? And the answer is you would need 3 pieces of information, 1 for each piece of the integral. So the first is on your principal major arc, you're going to need to understand that special zeta function. On the non-principal major arcs, you're going to need to understand how it behaves in residue classes. And on the minor arcs, you're going to need to understand these vowel sums. And if you have all of that information at your disposal, which is pretty rare for a set to have all of those information, but if you do, then you could run it through the machinery that is given in any of those results. So for example, in this paper of mine from 2021, and you could follow that method and get asymptotics for PA of n for that given set A.